today what I wanted to do was get sort of comfortable with this sensor. So there's a sensor that's used a lot in rockets, and it's called the BNO055. So this sensor here, it's an accelerometer. So we measure all of the forces that are acting on it. But I also think it has like a gyroscope inbuilt to it, and I guess it's just an accelerometer and a gyroscope, but it does all of like really nice sensor fusion to output like variables that are easy to use. So when I say that, I guess the most important things that we are concerned about in a rocket is the like acceleration, so how fast it's going. You can integrate that twice to get the distance, so it's like a kind of rough estimate of how high you go. And you also are interested in the orientation. So like here, you want to look back at your flight data and be like, okay, did my rocket stay straight throughout the whole flight? Was there some roll associated with the flight, or was it also kind of like oscillating and just like going all over the place? So this is the sort of like really basic sort of sensors that you want on a flight computer. And it gets really complicated when you want to do this like really, really well. Because if you're working with like an analog accelerometer, it will just output a voltage, like a tiny little voltage that's proportional to the acceleration that's acting on it. And so, it might be like for every G that the accelerometer experiences in a certain axis, you get like a couple millivolts change in the output of the sensor. And that can be hard to deal with, especially when you look at there might be a lot of noise flickering around on that on that millivolt signal, and then after you actually figure out the relationship between what millivolt means what acceleration, then you have to do the math on it. For example, like integrating it twice to get distance. There's a lot of different techniques that you can use to get that, but typically you end up with some kind of drift depending on what technique you use. And so all of that little noise is going to mean you're like slowly getting less close to the truth. And there's also like different ways to combat that. So in like control systems, you learn about things like the Kalman filter, where you can get different sensors, for example, acceleration, your gyroscope, maybe GPS, feed it all into the system that kind of combines them into one measurement. And a lot of the time that's a lot more of like a stable reading than what you would just get without doing like sensor fusion. So Kalman filters are a massive area of research. And I think what's great about this sensor is it does its own sensor fusion on the board. So what we want from this is what's called a breakout board, if you're not really sure. So this chip here, this is the sensor, and this whole board adds all of the peripherals that you need to make it work. So, here you just have to hook up power, ground, SCL, and SDA. These two pins here are for the I2C communication protocol that we're going to use. If you haven't heard of that, it's not too complicated, but we'll kind of go through that later. What we want on our flight computer when we're designing a PCB is essentially to design this whole breakout board. So we want to grab this chip here, say, okay, what components do we need around it to make it work? So that would be like capacitors, resistors, they've added an oscillator here, which, we can decide whether or not we want to do that. LEDs, plugs, and basically interface it to what we want to use as our like main controller. So rather than having a main controller on a different board, it's all integrated onto one board, and it's very nice and easy to use. So basically what we're going to do today is have a look at this sensor. We're going to go dig through the data sheet, because normally on the data sheet they kind of tell you all about what components you need around it, what voltages you're working with, and once we get into the I2C communication protocol, it'll tell you all of the registers that you need to read and write to get information out of the chip. Oh yeah. So I think I mentioned that this does all of the sensor fusion. So it's basically going to spit out some really nice information rather than like millivolts per G-force or whatever it is. This sensor here outputs your orientation in Euler form and quaternion form. Don't worry about if you don't know what either of these things are. You learn about them in dynamics. And quaternion is just usually what computers use to deal with rotations. It's not very intuitive, but it's very nice for computers to work with. So the sensor also spits out angular velocity, so that's from the gyroscope. And so you can integrate that, your angular velocity, to just get standard angle. And so that's what they're doing here. So the bunny basically matches what the sensor, or is trying to match what the sensor is doing. And so they're integrating this gyroscope. Acceleration vector. So yeah, typically this is also from the, angular velocity. You can read that, but it already does the integration because it passes out the absolute orientation. So you get this, integrate that to get these. Great thing about the chip is you don't have to do that. It's also got a magnetometer on it. So rather than using your gyroscope, integrating your gyroscope, you can use the magnetic field of the Earth. It's basically a compass, and that can tell you what your orientation is. We've got our acceleration vector from the accelerometer. We've got linear acceleration, and we've got our gravity vector, and I guess they just added temperature in here as well. So gravity vector is also good. That can tell you which way is up, and you can use that for all kinds of calibration. When you put your rocket on the pad to launch, you want to figure out which way is directly up. So, if there's some slight offset in how you put it down, at least it won't be flying at that offset. It can correct itself, I guess. If you're using, you want to get it as straight as possible, basically. We won't get into correcting anything just yet. So yeah, let's dive into like what this looks like, because for PCB design, you got to get really familiar with working with scary data sheets. And so if people want to find this, I just searched out BNO055. I just clicked here. Adafruit do a lot of good stuff with little electronics like this. If you wanted to, you can basically just like purchase one of these boards here from Adafruit. It's probably going to be like $40, $50. But we don't want to make things easy. We want to make things hard and learn what PCB design, because PCB design is very cool. So data sheet, scary data sheet. This is a 105-page data sheet. It tells you everything you could possibly ever need to know about this sensor. And it's very good if you learn how to read these things and like extract the information that you need. They're pretty scary when you first start using these, because you're like, 100 pages of this, how am I gonna figure anything out? But as you get more experience, you really learn the best ways to look through these to get all the information you need. So if I want to interface with a sensor, the first thing I'll do on the data sheet is look for a few things. I'd say the first thing I'll look for is what power the sensor runs on. For example, standard voltages for all sort of like integrated circuits are like 3.3 volts and 5 volts. So we're going to work in that kind of range. I think this here, this BN055 operates in the 3.3 volt range, and it will tell you that in the specification here, or electrical specification, or I think it's like electrical physical characteristics. So these are the first things you want to look for. And in all of this table, in all of this data here, we can see that the supply voltage for this is between 2.4 volts and 3.6 volts. So in this case here, with this sensor, if you put 5 volts into it, it will probably die. unless we find a maximum. Sometimes they give like an absolute maximum rating for different pins, but it might be referring to that there. Let's have a look. Power supply rejection. Yeah, so my assumption is that here it says the max is 3.6, so if you go beyond that, it's probably going to break. So that means this sensor, if we were to, like use a USB cable, we couldn't power it off a USB cable because the USB is at 5 volts. Feeding 5 volts into this, it's just going to break it immediately. So if we're expecting in the future to use like a 9-volt battery to power the electronics on a rocket, or like a LiPo battery, or some other, even a LiPo battery, you're going to want some sort of filtering. The voltage will normally be a bit too high for this sensor. So we want some way to step it down into the range that this is going to run off. This is also convenient because the STM32 that we're going to use as the main microcontroller, that is, it operates at 3.3 volts. So we can just expect that to work. We can see down here that our supply voltage is between 1.7 and 3.6 for the in and out, the I/O. So this is all good. And we're pretty happy with everything else. So we're starting at 3.3 volts. We can take a note down. We can note that down somewhere. I'm going to start a new project on KiCad. So just open it up maybe, and we want to, we want a new project. And we want to call this our flight computer. Here we go. And we'll open up the schematic. And the first thing we can do, well, I was just going to take a note that this is 3.3 volts. So let's not look at the library yet. Let's go down and see what outputs this sensor actually has, so what all of the pins do. So we'll go down, so big scary data sheet, this is telling you all of the different internal sensors, what their registers are, where you can find all the information. And we want to go all the way down. I looked at this earlier, and I know the pin out is towards the end of this data sheet. Here we go. So this is a sensor that's kind of hard to solder by yourself, because all of the pads, so the electrical connections which are going to connect to your PCB are beneath the actual chip. And so you might need like a hot air gun or something like that. But for now, just for like the sake of practicing this stuff, this is like a very good way to start learning how to do this sort of thing. So you can see pin 1 is here, and then we probably go all the way around because this is a bottom view. So that's where all of our pins are. Now, what do these pins do? That is described here. So you can see like common kind of pins. You've got your ground. VDD is just your power supply. Bootload pin is a bit more advanced. We won't touch on that just yet. And we're going to use, we want to communicate to this via I2C. So that's that communication protocol we were talking about earlier. And I know that they give an example further down, but we're going to use like COM port, or COM1 and COM0. So does it say where these pins are? These are 19 and 20. So we're basically going to want to route like traces of copper out from pin 19 and pin 20, and that's going to be our communication line. And then there's a few other things that we'll discuss. Now, Bosch are very nice, and they give us an example circuit for how you communicate to this thing via I2C. So this might be a bit confusing at the start, but most of the time, if you're looking to utilize a sensor, the company that produces the sensor will give you a rough idea of how to use it. So this is all of the different parts that we're going to want to put on, and we should be pretty safe to just like essentially build this in our schematic, and we'll be pretty confident that it will work. So the first thing to do, let's go back into KiCad. And KiCad is great. So honestly, we can just search for if this, there we go. We can search if that sensor exists within our library, and it does. It's great. So here we go. This is the schematic. It's got all the pins that we would want to use, and yeah, it tells you which you can connect and which you can't connect. This is great. Like, this is exactly what we want. Now, there's going to be sensors and there's going to be parts out there that do not exist in the KiCad library. And so in that case, what you'd have to do is look at this schematic and look at all of these pins. Okay, what's VDDIO? I'm going to go figure that out. And you can construct this schematic symbol from the data sheet. It's not that hard. It's pretty much, you know, there's nothing special about it. You just got to get your pin numbers right. So, you know, like for example, this here is pin 28, and you want to label it correctly. It's pretty much as easy as that. But it's already here, so we can just click that and we're good to go. So this is our sensor. This is our orientation sensor, and this is our accelerometer. So we'll be able to, if we're logging data from the rocket, we can tell its orientation at all times, and we can tell the distance and the forces that are acting on it. And these are all things that are going to, you know, help you iterate to build a better rocket. It's the information that you want to know. Okay, so we're at this stage, and we want to build this out to, we want to add all of these parts around it so that we can actually interface it with something else. Because at this stage, you know, where's the power going? Which lines here are we going to communicate to? You know, we're going to write it out to the microcontroller, but it's not as simple as connecting this pin to this pin. That's like, you know, otherwise you could just put the sensor here and be done with it. But all of this stuff around it is what actually makes it work. And so, yes, we're going to have to add that. Now, the good thing about sensors like this, you know, these are pretty like integrated circuits. They've got most of the complicated things internal, so we don't have to worry about putting transistors or op amps or anything like that to support its use. That's, you know, all internal. We just usually have to add passive parts. So we've got capacitors and resistors, and I think that's pretty much the only parts that we have to add around it. And that's pretty common for everything. So let's start by first, I'm going to move these. So I just hover over and press M. It's the beauty of KiCad. We want to provide power to this, and we want to provide a connection to SCL and SDA. So before I was talking about I2C, you know, if you Google I2C, there's going to be a million different explanations of what it is. You know, like it's bus 1982, whatever. Like we don't really care about that. All you really need to know about I2C is that there's libraries online which help you communicate over it. And it's nice because if you want to talk to, you know, 10 different sensors, you don't have to draw a separate line, a separate pin connection to each of them. So typically you'd have like a chip select, and you have an independent chip select to say, all right, I want to talk to this one, I want to talk to this one, and it activates each of them as you cycle through. But with I2C, instead of having, you know, if you have 10 sensors, instead of having 10 dedicated lines that go to each of them, you only need 2 lines to talk to all of them. So that's kind of what a communication bus generally does. You can talk to a lot of things over, you know, a few connections. So for I2C, the most important, well, the only lines that you need are SDA and SCL. So SDA, I'm not sure why there's an S at the start, but DA, I just remember this is like data. So this is where all of your data information is transmitted. And then SCL is just clock. So this is where your clock signal is every time. It's sort of just like a square wave. It goes up, down, up, down, up, down. And generally on every, oh, here we go. Yeah. So every time the clock goes up or down, it kind of registers whatever signal was on the data line, whether it was high or low. That's kind of like the indicator to say, all right, take a measurement of the line now. And that's pretty much how all clocks work. But let's go back here. Yeah, what we're interested is in SDA and SCL. So if we notice here, we know that COM1 goes along here to SCL. So this is where we're going to get one of our wires from. And the other one is COM0. So COM0 goes to SDA. So I'm just going to draw wires out like that, just to start. Now, the other thing we want is obviously power to the chip. And before we establish that, we have 3.3 volts. So if you remember, we'll go grab a power port, and let's just say we have 3.3 volts coming in here. Now, the other thing that we want is our ground. And this is where we're going to connect ground to the circuit. So this is just the ground pin here. Connect that. And so actually on this chip, we also have these VDD IO and ground IO. This is for when you're communicating with something, like you want to power the chip with 3.3 volts, but you want your communication signal to be at a different voltage. We don't have to worry about that. Everything's going to be running at 3.3 volts on the board, so we can just connect things like this. So that means, you know, on our I2C, the data, when you have like a high signal, or when you're transmitting a sequence of bits, you have a 1 0 1 0 1 0. That's going to be transmitted as like a high low high low high low, and the high, what we're telling him now is the high is going to be at 3.3 volts. So what's next? Now for I2C, there's another important thing that we have to remember. Oh yeah, we'll grab that in a second. So I2C has to use this concept called pull-up resistors. I can't explain it the best, but essentially what it does is it ensures that when you output a 0 or output a low from this pin, the signal is actually going to go low. You're not floating, if that makes any sense. So since this resistor is connected to our 3.3 volts, if we put a high here, we're going to get 3.3 volts here and 3.3 volts here, and everything's just going to be high at 3.3 volts. Then if we put a 0 here, this resistor is going to ensure that we have 3.3 volts here, and then 0 volts here, and it kind of just like completes the circuit, or it ensures that, yeah, this actually is low with reference to our power supply. And normally our pull-up resistors are a pretty big value. Yeah, let's just put in resistors for now. So grab our component. I'm going to use small resistors for now, just because I like them. I like these block tie resistors. You can also use like the classic zigzag. I don't know why they don't use that in KiCad, but it's kind of standard. So we want 2 of these on there, and I think if I press C, I make a copy. Yeah, there we go. Right, so now we're going to connect these wires up as so. How do we make this look not gross? It's going to be gross, don't worry about it. Cool. And so now we have like our pull-up resistors. Oh, sorry, actually. Let's just make them straight because these are going up to our power supply. So as you can see here, these resistors are pulled up to VDD. And so our VDD is 3.3 volts. So we can just chuck in 3.3 volts to these. Boom, and press C, make a copy. Cool. And now this is probably going to be a bit gross, but this is where we take our measurements for SDA and SCL. So if we just want to draw out little wires like this, we can see that, you know, SCL is here. It's at the bottom of the pull-up resistor, and SDA is here. It's at the bottom of this pull-up resistor. And so let me just check. COM0, it goes to SDA. What we can use is a global net label. So it's here, this little symbol here. And this basically just means, what do we want to call it? SDA. Yep. That we can put this symbol anywhere else, and it's going to act as if these wires are connected. So there's our SDA signal, and then we also want to put SCL. Okay. Let's make this a bit nicer. So I'm going to put that there, and I'm going to put this pull-up resistor like there. There we go. So that little green dot just means that's where it's connected. So these aren't connected here. Beautiful. So this is a good start. We're now powering the chip because we've got our 3.3 volts here, we've got ground here, and we've also broken out our communication lines. But that's probably not everything that we need to make this sensor work. It has a dependence on a couple of other things. So if we just go around the clock, around the chip, we've got VDD, VDD-IO, X out 32 and X in 32. These are for like an external oscillator. And so, you know, you might have like, I think it probably has like an internal, yeah, it's optional, an internal oscillator. So, you know, that's basically like your clock speed on a computer. It'll be like buzzing away, outputting all the information at a certain rate. You can connect an external oscillator to make it operate faster. I haven't done it before. It's not that complicated, but you just need to be a bit more careful with how you lay out your PCB. But yeah, that's what those weird things are. PSO, PS1, cap. What are these? So let's go to the data sheet and have a look. We've got PSO, digital in, protocol select pin, protocol select pin. So if we have a look here, what they do is they just connect it all to ground. So I'm guessing, yeah, it's basically just a way to pick what communication protocol you're using. And I2C must be 0. Let's get rid of one. Let's have a look. So it's basically going to be operation modes. No. Communication modes, where would that be? Output data, data output format. Probably that. So I think the way we're doing this now gives you a good sort of insight into what a lot of PCB designers do, and that's just looking through data sheets all day, trying to find information that you need. And honestly, you know, we don't even need this information. We can just copy it. It's just for the sake of being interested. Anyway, all right, let's just tie it all to ground. So what was that? PSO and PS1. It just says tie those to ground. So let's just do that. Hit this, ground, bonk. All right, and now there's a cap pin. So that's normally for like an internal reference. If you don't know, a capacitor, its general job is to smooth out a voltage. So if you're getting like a really, really high, or if you're getting like noise on a signal, it kind of acts as like a reservoir for voltage. And so it'll fill up to a certain degree, and it doesn't want to change its voltage. It wants to stay as consistent as possible. So if the input drops below some voltage, it's going to slowly let out its voltage to meet it. And if the input voltage goes up higher, it's going to slowly take in some of that voltage until it hits the same level. And so it's kind of just like a smoothing system for voltages. And so for internal reference, what you want is a very, very consistent voltage level, just like dead on, dead quiet, no like noise or anything. You just want it to be, you know, as nice as you possibly can have it. And so here it looks like they put in a 100 nanofarad capacitor on the cap pin. That'll just be for smoothing out some noise from whatever it is. So I think this is our first capacitor. Let's go place a symbol. I just press A, click, it comes up, and we can type in C small. There we go. That looks like it is polarized. So when I say polarized, you get capacitors that are, you have to put them around a certain way. Oh, that doesn't look, oh, that does. It says it's unpolarized. Oh, I'm sure it's fine then. So for example, ceramic capacitors, it doesn't matter if you put them around a certain way, they'll just work. And so capacitors of this size are normally ceramic, they're pretty small. But electrolytic capacitors, they're much bigger, they have a much bigger, what do you call it, farad. And so they, you have to put them around the right way. They're not going to operate both ways for you. So here we just put a capacitor and then we tie that to ground. What's the shortcut for power? P? Oh yeah, it is. Okay, there we go. Cool. All right, so, and now it told us in the data sheet where we want to put this. So we want to put a value of 100 nanofarad. So you can just put that there. I just press E on the actual symbol, it brings up all of this stuff. So there we go, we can see that this capacitor is 100 nanofarad. I have to look up what, let's just look that up now. I2C pull-up resistor, it's probably like 4K or something. It does depend, but you can usually get away with a certain value. They're getting all complicated on us. What is a good pull-up resistor? Frequency, so much. Generally 10K works. Yeah, I've used 10K before. So let's chuck that in. 10K. Obviously we can change this at any point. It's just for the sake of looking in the kind of the range. And so you can see here, even though you have 3.3 volts here and then potentially 0 volts here, that's going across a 10,000 ohm resistor. And so you're going to get hardly any current flowing through here. They just need it to work. Something to do with like open drain or open source, open gate, open drain, open source, something like that. You can look it up. Doesn't really matter right now. All right, cool. So we've got the cap, COM3, COM2. So what do they want us to do for that? COM3, COM2. COM2 goes to ground and COM3 is our address select. So may as well break that out. What was that, sorry? COM2, let's put COM2 on ground. Oops. P for power, and then COM3. So basically the way I2C works is every single sensor on the bus has a different address, and the way you talk to it is you put that address into the packet that you're sending out. And so there's normally an I2C address select. I'm not sure if you can tie this to ground and it'll be a different address in case there's a conflict, but they're normally like they're like preset addresses from the manufacturer. There's probably a way to change it, but we can probably tie it to ground and be happy with it, just work with it. Let's just put that on ground. Okay. Now, what are these other pins? We got all of these done. BL, I, and D. Blind. The blind pin. What's the blind pin doing? So sometimes the KiCad model doesn't perfectly match up with what you expect to see on the data sheet. It's because, I guess electrical engineers want to confuse people. We know we got bootload pin, that's probably this one. We've got our reset pin, which is this one. We've got our interrupt pin, which is this one. And then our BL, I, and D. Let's not worry about it. Can't say it. Do not connect, do not connect. Probably be all right. Oh, it's pin 10, so maybe that's another way to check. What's P10? Pin 10, ground, connect to ground idea. Great, okay. Let's do that then. Awful, that's all right. Now we've got pin 4, bootload. Pin 4, that uses a 10 kilo ohm pull-up resistor too, so let's just do that. Most of the time, like these things might not matter, but just for the sake of doing it, oh God, let's just chuck it in. I'm going to copy one of these across, and I'm going to copy one of these across, and then I'm going to put a boot net here. We've got our interrupt pin that probably just runs out. Yeah, we probably don't need that. And our reset pin, so we probably want to tie that high. Reset basically optional 10K. So we're basically with a reset pin, once you, if it's high and then you pull it low, it's gonna restart the sensor. So I think we want to just pull it high. Yeah. Oops. Let's just do that. I don't think we want to reset it ourselves at any time in the future, or at least at the moment. Cool. Okay. So bang, there we go. This is our initial prototype for our BNO 055 sensor. This should cover the basics that will make it work in on a board once we put it on a PCB. Obviously, when you look here, there's probably more parts. There will be more parts because this is breaking out like the interrupt properly. This is probably using all of the different communication protocols available to, like UART, and there was like some other weird one. It's probably allowing for all of that. See, there's like a transistor here. Don't know what that is. It's probably a step down regulator. This giant thing, I don't even know what that is. So this is like very robust. This is awesome, but we wouldn't need all of this on our board. We just want to pick out the specifics that we really need. So I guess we've done this so far. The next thing to talk about would be powering it. But before I do that, let's just like get it onto the PCB and see how it looks with all the parts. So remember, the first thing that we have to do is annotate. Okay, all of our resistors are numbered, capacitors are numbered. That's right. Oh, one more thing I forgot. There's probably some other capacitors that we have to add on the input pin. I2C connection. Yep. So here there's 100 nanofarad between VDD and ground. So let's just copy this across here. Oops. definitely want to learn how to make schematics beautiful and not rush it in an hour like this, but we're doing it live. And now these capacitors here, one is going between, it looks like they're both going between VDD and ground.io. VDD.io. Look, it's probably not that useful, but that's just to smooth out our IO lines. Honestly, what I'd regularly do is add another capacitor on the input voltage here, like a 1 microfarad, and that smooths out not the high frequency noise. It normally smooths out the slower noises first, but we don't have to worry about that right now. Let's work with this. Let's just get it on the PCB. So we've annotated everything now that we added that capacitor, and now we want to do our footprint. So if you remember last week, we talked about different footprints for our passive components. So these are like our resistors and capacitors. There's like 04, 02, 08, 05, just different sizes. Oops, open Spotify. Different sizes for our passive components, which are our resistors and our capacitors. So we're just going to give them some standard footprint. Oh, our boot lines got connected. We don't want those. Once this loads, we'll fix that up. These like little green dots. Yeah. Come on. We'll give them, yeah, pretty like standard footprints, and then we'll figure out what footprint this sensor uses. So I think it just said here, it's like an LGA. But maybe we can find the exact package down here. So here we go. This is talking about the external oscillator. You can make it operate at a higher frequency. Package LGA something. Done yet? Footprints always take ages to load. I think it's the 3D library that comes along with it. Let's keep looking. LGA. Might just come along with the right footprint as well. KiCad does that sometimes. Hello. LGA package 28 pin 3.8 5.2 1.3. Okay, see, this is why you got to get used to using data sheets, because the information I was looking for was literally right there. But let's not look at Spotify. Our footprints are nearly done. Oh, good old KiCad. You guys want to see something cool? This is satellite imagery that you can just download off the internet. This is an image from Sentinel-2 satellite just orbiting. And it's an image of bushfires from the start of this year. You basically just like download the channels directly from the satellite. So there's 13 channels, which represent like red, green, blue, and then you can compose them together into this kind of image. Cool thing is if you go to like the infrared band, look at this. This is like the fire burning down there. So if you like compare it to like all the smoke here, all the burnt area, fire. Come on, all right. All right, beautiful. So Banner already has the right package specified. So let's just chuck on some basic capacitors, capacitor, SMD. We just want, I like 0805, so I'm gonna stick with that. 0805 on those, and then we'll go chuck our resistor Aluminum 0805 hand solder. Cool. Okay. So now all of our footprints are assigned and we can generate a net. So we'll generate our net list. Let's just save it with its default name. And then once we go back here, I don't have an autosave. Weird. Let's open our schematic. And real quick, let's just define our board size. So remember, click edge cuts here. I think this is our line tool. Let's just draw something. So length, let's make this like, so actually up here you can define your grid size. And so, there's also a way to switch between metric. Oh, here we go. Inches, mils. Let's do our grid 5 mil, and let's just do a line that's like 80 mil, 8 centimeters, maybe 100. 100 by 50. Oops, let's do it like 100 tall. I don't know, you can decide whatever you want your flight computer to look like. This is just for reference anyway. Okay. Let's go back to mils, and we want our grid size to be like 5 mil. All right, so this is that, and now we want to load our net list. So remember, we got to click this button here to load it, and we'll just select our net list from here, update PCB, and yep. Here we go. So these are all our parts that we're going to be working with right now. This is our sensor. So this resistor, this capacitor, and you can see these net lines. They tell you where you have to connect in between on the PCB. And they're probably going to be a bit funny right now because we don't have like a ground plane or a power plane to connect things. One of the big things about PCB design is arranging your components first. Oops. So what I mean by that is, internet's bad. Let me know if I'm cutting out. Yeah, component placement is probably one of the most important things. You want to get them all sort of roughly in a logical manner before you start routing. Otherwise, your routing is just going to be very difficult. So another thing that you generally do on a 2-layer board is have a ground plane. Basically, this means like you have a massive connection of at field zone. Is just like a big polygon of whatever connection you want. So basically, what I'm going to do is put ground on the bottom layer of this board as such. Make it neat, fine. Okay. And now everything on the bottom of this PCB is now ground. So if I want to connect, for example, this capacitor here, now we're on the top layer, and I want to route a trace, I want to connect this to ground somewhere, right? I'm normally connected to here. But now that we have ground on the bottom, we can actually just place a via. And what a via is, oops, oh God. It's basically like a little tunnel that connects different layers together. And so if we just draw it out like this, and then click this button here to add a via. And now we've successfully connected, or maybe we'll just like get rid of these. We've now successfully connected a hole between the top layer and the bottom layer. So now if we look at this in 3D, you can press Alt-3 to do that. You'll see this tiny little hole right there. And that is connecting anything from the top layer all the way around to the bottom layer. And I probably haven't done something with the bottom layer, right? I've added a fill area, add filled zone, tools, inspect, place. Okay, let's fix this up. So I'm gonna get rid of this. I'm just gonna add a, so BCU. I'm just gonna add a polygon, I think, using this. Let's just like connect it like this, see what happens. Goodness gracious. What was this? So that's gone on that layer. I'm gonna put that on the bottom layer. Cool. Okay, so now if I hit B, basically it's going to fill in these yeah, we want to connect that to there. It's going to fill in that polygon and connect it to this via. Now, it's probably not working because I haven't defined what net it is, or this polygon is just graphic. It doesn't actually do anything. Normally they're called something else. Let's just have a look. We want to do a ground pour in KiCad. Copper pours. Oh yeah, so what's this? Anyway, what we want to do now is all the grounds, we want to connect them all up. We want to connect all of the resistors to the right part that we want to. So we'll define where the power goes, we'll define where all like SCL goes, our communication lines, and we'll basically have a little component of the board that is working. I'm going to fix up something real quick before the end of this, and it's these little green dots. Junction. So I'm just hovering over, pressing delete, because they shouldn't be connected. And then remember, we're going to generate our netlist again. Save that, go over to here, load our netlist, update PCB. And now, yeah, so this is our SCL here, SDA there. So this is going to make a lot more sense to connect things kind of like this. And we'll run our trace like this, run our trace like this. They're going to 3.3 volts, which we'll do next week. We'll define all of our power requirements next week. because it's a bit more complicated than you may initially guess. Now, normally for capacitors, you want to put them really close to the pin. So we'll nearly finish up here, but this is pin 28, 3.3 volts. Yeah, make sure that we're powering the proper pin. So VDD is pin 3. Oops. I'm going to move this capacitor down to pin 3. All of these text is getting really annoying. How do we close those? There we go. Now we're working with bare bones. And connect this to this. That's the boot pin. This is just connecting to there. Ground, we want to put wires in here, but let's just connect them up for now. Ground, 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 ground. And you can do the rest. Just wire these up. I mean, it's pretty much as simple as that for the moment. You just want to make sure there's no more rat lines, no more of these blue lines. Blue, white lines. You can go on the inside, that's totally fine. This has to go to ground, so you can put another wire in. Just click that there. That has to go to ground. And then you see where it can get complicated now is, okay, what if this pin here, what if I wanted to connect this pin to this pin here, pin 2. Now I've routed it in a bad way because I can't just draw a direct line. I have to go all the way around here and then all the way around here, or I've got to go, you know, there's like trade-offs to everything. And normally to solve this, we use the back layer of the PCB because that provides like a whole extra dimension so you can run traces under each other. But it gets complicated quickly and it can be very difficult to route some things. It just takes a lot of planning ahead to do it right. Anyway, that's sort of an intro to this PCB design. We're not really going to cover software in this series because that's a whole different story in of itself. But you know, to interface with this sensor, you're going to have to look at the data sheet, and you're going to have to figure out these, depending on what kind of level you're looking at using it at. You might have to use all of these registers to get the information that you want. Here, gravity, data, in a Y direction, most significant bit is at register 0x31. This is how you pull the data from it. But we're just going to do the hardware. So hopefully that kind of helped. I'm going to clean this up for next week, and then it will just be easier. I'll upload this so you guys can just download it once it's cleaned up, and we'll slowly build this out. We'll have this sensor. We're going to do our power circuitry next week, and then we'll deal with the STM32, the big old bad boy, and then we can add whatever else we're looking to add after that. Yeah, thanks for coming through, guys. This will just be uploaded to YouTube, so feel free to go back if you missed anything, and shoot me a message on Slack.